I'm back again. This time I'm going to just discuss some common forces that show up in physics problems, and then we're going to discuss using free body diagrams and solve an example problem using free body diagrams. All right, so there are some common forces that come up again and again, and probably the one that comes up the most in this class is gravity. We will learn later on Newton's law of gravity says that if I have two objects, one with mass m1 and one with mass m2, the force of object 1 on object 2 due to gravity has a magnitude which is equal to a constant, g, times the product of the masses divided by the distance between the two objects squared. Now, we'll get to that later in the course. For now, most of the problems we work will be things falling under gravity near the surface of the Earth. And when we're near the surface of the Earth, you can just approximate the force of gravity as being a constant. The force of gravity is just equal to the mass of the object it's acting on times a constant g, where g is the acceleration due to gravity near the surface of the Earth. Now we need to distinguish between mass and weight. So mass is a property of an object, and it has units of kilograms. If you know the mass of an object, that it's its mass wherever you put it. The weight of an object, however, refers to the force due to gravity acting on the mass. It has units of newtons, which is the same as kilograms meters per second squared. The weight of an object depends on what the force of gravity is. So your weight on the Earth will be different from your weight on the moon because there's less gravitational pull from the moon than the Earth. However, your mass is the same, whether you're here or on the moon. Now, it turns out that there's really two different things we mean when we say mass, and we tend to interchange them. There's inertial and gravitational mass. So, remember, when we learned Newton's second law, we said force is equal to mass times acceleration. So basically, mass is limiting how fast we accelerate. Mass gives us some inertia. So the more mass you have, the less you accelerate for a given force. So that is what we would refer to as inertial mass. All right? So inertial mass, because of our inertial mass, the acceleration that we experience is force divided by mass. So if I have an object with a certain mass, this acceleration is the force I apply to it divided by the mass. And the more mass it has for a given force, I will get less acceleration. So that's the inertial mass. But we said for an object near the Earth's surface, the force due to gravity is just mg. So let's imagine I have an object and the force that's acting on it is gravity. So the force is mg and the acceleration is force divided by mass. So the acceleration is mg over m. And so the acceleration is just g. The mass cancels out. So you can kind of see there's two different roles mass is playing. In the top, in the numerator, that is gravitational mass. So there's this force that is proportional to your mass. In the bottom, you have inertial mass. You have your inertia, your tendency to not want to accelerate. Okay? And they just happen to be the same thing. It's kind of weird that they're the same thing, but it's important to remember that there's two different things. There's inertia, and there's the thing that causes gravity, and they just happen to be the same. Because physics wanted to be weird, I guess. All right, another force that we'll deal with often is what we call the normal force. And the normal force is the force that pushes upward on something from a surface. We call it the normal force because its direction is normal to the surface or perpendicular to the surface. That's what normal means. So something that is normal to a surface sticks out of the surface at 90 degrees from the surface. So the normal force is the upward force, or the force which is normal to the surface. So for example, if I have a block sitting motionless on the ground, gravity pushes down on it. The force of the Earth on the box is gravity. That pushes down. Well, why doesn't the box accelerate downward? Well, the ground is pushing up on it. The normal force cancels out gravity. So the normal force on the box cancels out the Earth's force on the box. If the ground is inclined, so imagine we have a box sliding down a slope. Right now, the normal force is going to be normal to the surface. So now gravity and the normal force cannot cancel out because they're not in the same direction. But I can write gravity, the force of the Earth on the box due to gravity, I can write that as a component along the direction of the slope and a component normal to the slope. And so now the normal force will be just big enough. It will increase, right? The more you push down on something, the more the ground pushes up. So the normal force automatically grows to be as big as it needs to be to keep things from going through the surface. So in this case, the normal force cancels one component of gravity, but we're left with the component of gravity along the surface, which can make the object accelerate. Another force is friction, and we're going to talk more about friction later on, but you should know that there are two different types of friction. So static friction keeps things from moving, but then once things are moving, dynamic friction tends to slow things down. So for example, if I have a box and it's sitting still and I push on it, static friction counters the force that I apply to keep the box from moving. So as I push harder, static friction gets bigger. And it's like the normal force. It gets as big as it needs to be to stop the box from moving. But just like the normal force, right? If you put too much weight on a surface, it'll break. If you push too hard on something, the static friction force cannot stop it from moving. So if I exceed a maximum level for the static friction, then the object will start to move. At that point, static friction no longer exists, and we get what's known as dynamic friction. And dynamic friction, it turns out in the simplest model, which we will discuss later, is just proportional to the normal force, and it is opposite of the direction of the object's motion. It goes opposite direction of velocity. Tension is the force that we describe from a string. So imagine I have an object suspended between two buildings by a string. So tension is the force of the string on something. So the tension force on the object from the string to the right, tension always points in the direction of the string. So the force of the string on the building on the right, also along the string. Strings can't push, they can only pull, they can't move things to the side, they just pull. The rope on the left, it has a tension force which is pulling the object in the direction of the string, and it's pulling on the building in the direction of the string. Now, sometimes we'll do problems that involve pulleys, and pulleys are just little wheels that are free to move. So if I have a pulley and the friction of the pulley is very small, so the wheel moves very freely, and if the mass of the wheel is very small, then the tension on both sides of the string will be the same, right? Because if the force on one side was bigger than the other, that would move the wheel, it would make the wheel rotate. And so the wheel will rotate until the two forces cancel out in the tangent direction, the direction tangent to the surface of the wheel. So when we have a pulley, the tension on either side of the string is the same, but in opposite directions. Well, they're in the direction of the string. Okay, drag is kind of like friction, but for fluids, where fluids are gases and liquids. So if you have something falling through the air, you get drag. And spring forces. So if I have something that's springy, like a spring or a piece of rubber, it has a natural relaxed length. The kind of it's natural. If you're not squishing it or playing with it, it just wants to be a certain size. And then Hooke's law tells us the force that this springy object creates if we move it from that relaxed length. And Hooke's law says that force is minus kx. K is a constant for the spring. It's known as the spring constant. So it's a property of whatever spring you're using. And then x is how far you have displaced the length of your spring from its relaxed or equilibrium length. So note if you change the length in one direction, the force is in the opposite direction. So for example, if I stretch the string out, I move the right side of the string, pull it out, and I've displaced it by an amount x, the force is going to be equal to minus kx. So it'll be in the opposite direction from the displacement. So the force will be that way. Now the spring also pulls on the thing it's connected to on the other side, once again, in the direction that tries to bring the spring back to equilibrium. If I compress the spring, all right, so if I squish the spring, now x is negative, but the force is positive, right? The force is in the positive x direction. It's trying to, once again, move the spring back towards equilibrium. And the force on the other side of the spring also tries to expand the spring, bring it back towards its relaxed length. There are also various fictitious forces that show up in physics. They're not real, but they're useful sometimes. They are the result of accelerating reference frames. For example, imagine you're swinging a ball on a string. Why does the ball stay out at the end of the string instead of getting pulled in? Well, the answer is that's the wrong question to ask. I mean, there's no reason for the ball to come inward, right? If the ball were on its own, it would fly a straight path. But the string pulls on the ball and keeps it from going on the straight path and makes it curve. So there's really no reason to expect the ball to come in. However, if we're doing physics in a rotating reference frame, so imagine instead of swinging the ball over your head by moving your arm, imagine you're turning in a circle, and so you're turning with the ball. In your reference frame, the ball always stays right in front of you, right? It's not moving. So why doesn't it fall down? All right, why does it stay out? So what you do is you make up a fake force to take into account the fact that you're in an accelerating reference frame. You're in a reference frame where the standard rules of physics don't really apply. All right, so again, spinning spaceship. So imagine you have a big ring-shaped spaceship and you make the ring rotate, all right? And then people can stand on the surface of the ring and it's like there's gravity there, all right? And they're like, oh, there's this force pulling me downward. Actually, no, there's no force pulling you downward. You're moving with the ring, which means you have a velocity, and your inertia wants you to go straight, flying off into space, but the surface of the ship pulls you back in, right? And so it feels like there's gravity pulling you down, but there's not. But, you can make things up. You can make up these fake forces that take into account the fact that you're in an accelerating reference frame. Another example is the Coriolis force, right? So I shoot an artillery shell and I try and hit a target and I miss. If my artillery shell is in the air for a reasonable amount of time, guess what? The Earth's rotating. And so even though I calculated I knew exactly how to aim my shell, by the time my shell gets there, the Earth has moved and I hit the wrong point. All right? Now, is there really a force on my shell moving it to the wrong spot? Well, no, right? It's just that the Earth moved. However, if I want to do calculations relative to the Earth, I can come up with this fictitious Coriolis force that I can add in to help me aim my artillery that accounts for the fact that I'm actually on the Earth, which is accelerated. I'm going in circles around the Earth. And hurricane, same example. There's a low pressure, the air tries to rush in to fill it, but the low pressure place moves because the Earth's rotating and you get the swirling. So once again, the Coriolis force doesn't really exist. It's not really a thing. It's a made up mathematical thing that we put into our equations to make up for the fact that we're trying to do physics in a non-inertial reference frame, in a reference frame that's accelerating. Here's another example. So a car accelerates, you get sucked into your seat. It's as if the seat is sucking you backwards, right? No, right? The problem is you're in an accelerating reference frame, all right? The laws of physics, the equations we come up with, Newton's second law and such, apply to non-accelerating reference frames. So you can make up some fake things. Oftentimes, it's better not to mess with fictitious forces because they can be confusing. Just work your physics in a reference frame that's not accelerating, and then take your results and transform them into the accelerating, rotating, or whatever coordinate system. So anyway, don't get confused. Centrifugal force, Coriolis force, they're not real. They're just useful mathematical things. Okay, so now we're going to talk about free body diagrams. Free body diagrams are a way to simplify physics problems and help you work them. A free body diagram is very simple. You just take each piece of the system that you're trying to understand, and each piece you write a little description of a dot or something that represents that object, and then you draw all of the forces that act upon it, and then you label each of these forces, and then you can figure out how that object moves. Very simple, right? So let's do an example using free body diagrams. Imagine that I have a cart, it's this red block here, and it's sliding on a track without friction. It's being pulled by a string, which is making it accelerate. That string goes over a massless, frictionless pulley, and then is connected to a weight in blue here, all right? So the weight, gravity pulls the weight down, that pulls on the string, which pulls on the cart, and the cart accelerates. And I want to find the position of the cart as a function of time, right, as it moves from its initial to a final position. So how do I do that? Well, we're going to draw free body diagrams. Now, it's tempting to draw, when we do our diagram, to draw the whole system, but we're not going to do that. We're going to, for each mass, we're going to have an individual free body diagram. So for the cart, I'm going to make a little spot here. I've got a cart. It's got a mass M1. And what are the forces acting on my cart? Well, there's the force due to the tension in the string on mass 1. There's also gravity, the force of the Earth on mass 1. And then there's the normal force from the track. So the force of the track, normal force on mass 1. All right. Now, then on the second object, the weight, it has a mass we'll call M2. And what are the forces acting on the weight? Well, there's the force of the Earth on mass 2, the gravity acting on the weight on the downward direction, and then there is the force of the string's tension acting on mass 2 in the upward direction. So now we have these two separate free body diagrams, and we're thinking of the two objects separately, and then we'll discuss how they're connected in a moment. So let's start with the first free body diagram. First of all, we know there's no acceleration in the y direction. The cart is just sliding along the track horizontally. So we know that the force due to the Earth on mass 1, the force due to gravity, plus the normal force on mass 1 have to add up to 0. But that's kind of boring. So let's talk about the x component now. So now there's only one force that has an x component, and it's in the x direction. So let's just drop the vector signs, and we'll say the force, we're just using Newton's second law, right? F equals ma. So the net force on the object is going to be the force due to tension on mass 1, and that's equal to the mass 1 times the acceleration of mass 1. All right? So if I knew what the force due to tension was, I could find the acceleration, and I'd know how the cart would move. But if we look at the full system now, there are a few things we should note. First of all, since we have a massless, frictionless pulley, or something whose mass and friction are negligible, that means that the tension on both sides of the string are the same. So that means the force due to tension on mass 1 is equal to the force due to tension on mass 2. Furthermore, if we assume that the string can't stretch, that means the mass and the cart have to move together. If the mass moves down by 1 centimeter, the cart has to move to the right by 1 centimeter. So that means if their motion is the same, their acceleration has to be the same. So the acceleration of the cart has to equal the acceleration of the dangling mass. Now, we have to be careful about sign conventions, because as the cart moves to the right, the weight moves down. So I'm going to define positive motion for the cart to be to the right and positive motion for the mass to be downward. Okay? Now, let's look at the free body diagram of the mass 2. Well, we know that the net force is equal to the mass times the acceleration. So gravity, the force of the Earth on mass 2, plus the force of the tension in the string on mass 2, that's the net force, so that has to equal mass 2 times the acceleration of mass 2. Well, once again, we're going to define downward to be the positive direction for mass 2, and then I can get rid of my vector signs, and I'll just say, gravity is downward, so that's positive, tension is upward, so that's negative, and that has to equal, the sum of those two has to equal mass 2 times acceleration 2. Of course, the force due to gravity, the force of the Earth on mass 2, is just mass 2 times g, right? Also, we know that the force due to tension on object 2 is the same as the force due to tension on object 1, and we know the acceleration of object 2 is equal to the acceleration of object 1. So now we have an equation with the tension and the acceleration of object 1. And remember before we said that just using F equals ma on object 1, we said force due to tension on object 1 was mass 1 times acceleration 1. So we can plug that in for the force due to tension in the equation above. And then we can just solve this by first taking all of the stuff with acceleration to the right-hand side. So we'll add m1a1 to both sides. And then we get this. Mass 2 times gravity equals m1 plus m2 times acceleration 1. So before we solve this any further, let's stop and think about this. This kind of makes sense, right? This is F equals ma. So basically the kind of the net force that's acting on the masses connected together is just gravity, right? If we kind of think of them as now as one unit, gravity is pulling on this whole assembly, all right? But it's only pulling with a force equal to m2 times g, because the force of gravity on the cart is canceled by the normal force. But the inertia of the system consists of both of the masses. So the gravitational force only depends on mass 2, but the inertia of the system is due to both of the masses, m1 plus m2. So anyway, let's move forward. We can solve this by dividing both sides by m1 plus m2, and we find that a1 is m2 divided by m1 plus m2 times g. We can get rid of the 1, right, because the acceleration is the same for both objects, so we'll just call it acceleration. So the acceleration is m2 over m1 plus m2 times g, and it makes sense, right, because in the limit, as m1 goes to 0, if there's no cart, then the mass ought to just fall, and we get m2 over m2, or just g, right? And in the limit, as the cart is really, really big compared to the mass, compared to the weight, then we expect very little acceleration, right? And in that limit, the acceleration goes to 0. So it seems to make sense. Okay, now I wanted to find the position. So to find the position as a function of time, first I will integrate this to find velocity, and then I'll integrate again to find position. And there's my solution. I just need to know the initial position and velocity and plug it in, and I know the position at every moment in time, and then I can make a beautiful animation of the cart accelerating as it's pulled on by the mass on a string. And that's the end of our discussion for today.